Okay, welcome to Information Theory, Lecture 26, February 3rd. And I'm sure all of you last night were out on the streets, either in Pioneer Square, ripping street signs off their street posts, or lighting bonfires up on Fraternity Row, celebrating your victory, your personal victory over the people of Denver, who personally lost.
In fact, the majority of the country is on the other side.
That's right. So enjoy your victory. I think the good news about this, from our perspective, is that more students are now going to be wanting to come to the University of Washington, universally. So today what we're going to be doing is talking about rate-distortion theory and the alternating minimization procedure, in particular for computing the rate-distortion function. This is the last day we're going to spend on rate-distortion theory, by the way. And then on Wednesday we're going to start a completely new topic, which is complexity, other measures of complexity, measuring complexity. And that's, if you haven't been following the rate-distortion stuff so much, or this far, this is a good chance to sort of reset and begin again. So we have our current reading, and also our extended reading. So today we can talk a little bit about this, but most of the stuff that we're going to be talking about is drawn from this source and also this source here. So these are really the two sources that we're going to be drawing from. The other thing I want to mention, I'm going to mention this right at the beginning. Well, let me just finish the preamble. So there's still no outstanding homework. Also, we normally have office hours on Mondays, but today unfortunately, I have to do an extra amount of carpooling, and so there's no office hours today. But I will do makeup office hours, or alternatively, as always, maybe this is even better than office hours. Feel free to hang out with me on Google, and I'm happy to hang out. Just a reminder about the final presentations. This is something that we went over in some detail last time, but I want to remind everybody about these deadlines. The first one being February 17th, which I think is in 2 weeks from today. Is that right? Okay, so the first deadline is 2 weeks from today. And so just to remind you about this. So you should be thinking about this now. And if you have any initial ideas, just email me or something. But you might want to just start reading now. I'm hoping that by 2 weeks from today, you've read a number of papers.
You were lying that you have to look at a lot of abstracts to find the...
Yeah. No, I'm not lying. I think hopefully if everybody looks at 200 abstracts, then maybe you're doing a good job. Okay, so what we're doing today is we're talking about computing the rate-distortion theory function. And here's the actual function. And what we want to do is come up with sort of easy and simple strategies for doing this. Now, actually, last time, I actually taught this material once before. And last time I prepared a lot of extra material on not only the theorems and the statements of the theorems that we need to go through, but also going through all of the proofs. And today, what I've decided to do, because I think that while the proofs are interesting, it wasn't as I ended up spending like a week and a half going through these proofs. And I think that the students didn't get as much out of the proofs themselves as they got out of the statement of the proofs. And so today what we're going to do is primarily go through the statements of the theorem. The proofs are there in the slide, so if you want to go through the proofs, you're happy to do so. But I'm only going to go through them very superficially, if at all, because a lot of them get into some of the finer points of measure theoretic arguments and the radon-Nikodym derivative and those sorts of things, which I think one should at some point understand, but I think in the context of this class, since we're not a measure theory class, nor are we sort of officially an optimization class, we should sort of stay focused on the goal of information theory. And in particular, the actual thing that we're going to be proving actually turns out to be a very simple algorithm. And I think if everybody comes away with understanding that for this particular function, computing R of D, and for the channel capacity function, and for a number of other functions, that we're going to talk briefly about, but some of which might actually come up. The alternating minimization procedure is, on the one hand, it's an extraordinarily simple method that sometimes is very, very efficient, and then sometimes also is guaranteed to give you the correct answer. And the rate distortion function turns out to be one instance where it's guaranteed to give us the correct answer. So this is a very, very useful thing to have in your toolbox, your optimization toolbox, because it's just such a simple and effective method that works for real problems. So here we're going to, our sort of goal is, again, motivated by the rate distortion function, but we're going to see how this works with the channel capacity function. So last time, what we derived when we expressed it as an optimization problem was the following update, which was this. And we saw how the conditional distribution, so remember what we're optimizing over in the rate distortion function is this conditional distribution here. Right? That's the guy we want. And so that guy can be expressed very easily to be, proportional to the marginal. It's a q of x hat, which is the marginal, times e to the negative distance, which we saw makes a lot of intuitive sense, because highly distortive pairs of symbols should get a low conditional probability and vice versa. Things that are that don't cause so much distortion shouldn't have a low probability. So we did a little bit of algebra, and we found that we can come up with number of equations and a number of unknowns. We have these unknowns, and then we have the distortion, and then we can actually use this to solve for this marginal distribution using Gaussian elimination or something else, constrained Gaussian elimination. And we saw this theorem, in fact, that sort of more formally proved that if any one x hat is 0 for a given x, then they're all 0 for all x's. And so therefore we can completely eliminate that code word. And we also saw how that happens more often when the distortion is high, because eliminating code words means that the rate gets to decrease. And at some point, of course, the rate's going to go to 0. And the way that happens is by essentially there being code words that never get used. And that happens in this conditional probability distribution by setting those values to 0. So we looked at this theorem. We proved this theorem last time. And we also didn't prove, but we talked about how the remaining Lagrange multiplier can be seen as the negative of the slope of the rate distortion function. And so one way of essentially computing the rate distortion function is to carve out these different points in the slope. And then we get, as a result, RD pairs based on these formulas. So there's the D and there's the R. And these are the things that, they're based on the solutions that we've actually acquired, because they're based on Q of X hat, which we have to get. And this is also based on Q of X hat. But once you've got Q of X hat, you can essentially plug in those values into these formulas and get a particular RD pair, which basically gives us one point on this curve down here. This is also from last time. There were some trickery that we had to deal with regard to the fact that when we relax the constraint, sometimes these marginals become negative, which then means that we can just project them back onto the convex set, which means that the closest point is going to be 0, and then we have to resolve the equation, and we sort of repeatedly do this over and over again. The problem is that's somewhat sort of tedious and hard, and what we want to do is sort of define a much better way of doing that. And so this defined this idea of the notion of alternating minimization. Sort of the general idea is the following. We have some distance or divergence or something, some d, which might be even just a quasi-distance. And I'll talk about that in a minute. And the goal is to essentially construct this optimization. We want to jointly optimize over A and B and find the minimum. And the algorithm can be seen as follows. In some sense, it's a little bit like a coordinate descent. But we're not necessarily saying, in general, what we're not going to necessarily say is, say, D is jointly convex or anything. We're going to think of this algorithm as essentially a way we have some objective, or some D, which takes 2 arguments. And what we do is we alternate between holding A fixed and optimizing B, and then holding B fixed and then optimizing A. So it's a very simple procedure. But what we want to do today is get a little bit of a sense, at least. I mean, you know, how general can D be, and how general can the sets A and B be for this procedure, the alternating minimization procedure, to assuredly give us an A and a B at the end of this procedure, if it ends. You know, when is it going to converge? Is it going to oscillate forever? But if it ends when the resulting, say, B infinity and A infinity, the A and B that we get at the point of convergence is such that when we plug it back into D, we get D min. So what's the least we can assume about D, about the sets A and B? And moreover, does that include, in our case, the Kullback-Leibler divergence, which, as you know, is not a Euclidean distance. So so here's the statement of the question we want to try to answer based on what I just said. So we take the limit and A star, B star. So A star, B star is, you know, the point at which these values get if they do converge. Because, you know, like I said, there's no guarantee that we're going to have convergence. So these are the star versions, and we want ideally this to be the case as well. Okay, so we started outlining. This is actually one theorem I do want to go through because it's not so hard, and it's important, and it's related to Kullback-Leibler divergence, which is the notion of these projections. So we could think of the Kullback-Leibler divergence as, in some sense, like a distance-ish like thing that measures the distance between two probabilities, although it's not officially a distance, as I will mention in a minute. But in this particular case, what we're trying to optimize is just this part over here on the right. Right, so we have the Kullback-Leibler divergence. Notice that P of x is fixed. Right, so we're not optimizing over P, and also P of y given x is fixed. What we're doing is we want to find the R, the probability distribution over R, such that this factor distribution P of x times P times R of y is equal to this distribution, which is really just any arbitrary P of x, y. And we optimized this, and we found that the one, what we're saying is that the R star that achieves this is the one that's basically equal to the marginalization, which basically means that marginalization is a form of projection using the Kullback-Leibler divergence, which, you know, might on one hand seem obvious, but on the other hand it's something that definitely is in need of a proof. And then the second instance we have is that, let's look at this. So we're going to do this a number of times. We're on the bottom part now. We're going to zoom into this part over here. Okay. So zoom in over here. I mean, this is also, you can think of this as a Kullback-Leibler divergence because you can always add some other, say, P of y here. Right, but we're not going to do that right at this instance, because, you know, as long as you multiply it by 1, it's the same thing. But the point is, what we're doing is we're optimizing over this conditional distribution R, and we have this joint, which is any P of x, y that's factored in this particular way, and then we could multiply that in by P of y if we wanted to, which I've just done. And the, you know, P of y would be the marginal. And the question is, what conditional R of x, y achieves the minimum in this Kullback-Leibler divergence? Does everybody see how this is a Kullback-Leibler divergence here? When I multiply in P of y. It's so beautifully written, I can't imagine you not seeing. So let me fix this a little bit. So if I write this as P of y, P of y, and then just to highlight a little bit. So you see how that bit is Kullback-Leibler? This right here. So we're basically within the Kullback-Leibler, we've just got one bit of it that we're optimizing over, which is this part, which is that part right there. And it turns out that is equal to the RY that achieves it is this marginal up here. just P of xy. It's just the conditional distribution that's formed from the joint. So it's a form of marginalization, although we just, we're dividing by a marginal, P of y. So how do we prove this? I mean, well, actually, let's before we prove it, let's talk about this from the perspective of mutual information, because we do know that there is a relationship between the Kolbeck-Leibler and the mutual information, right? And so let's write the mutual information in its definition form. And the Kolbeck-Leibler, the mutual information is equal to the Kolbeck-Leibler between the joint and the product of the marginals. And so that's what's written up here. We've got the joint and the product of the marginals. And so we can then write this as a minimization, because P of y is the distribution that achieves this minimization. But we can also write this as a maximization, because P of x given y is the conditional that achieves this maximization. And so, as a consequence, we get this bound. Whereas if we plug in any r of y and r of x given y, we get that the right-hand side is always going to be greater, and the left-hand side is always going to be less. Okay, so it gives us an interesting thing, an interesting sort of set of tools right away that we can, for example, use if we want to minimize different aspects of, say, of the mutual information. Maybe we can sort of minimize arguments of it rather than writing it this way. Sort of, in some sense, it's like an optimization variational-like framework to express the mutual information. So first of all, let's prove the first part. So let's go back to remind you what the first part is. The first part is basically this part. This part here. Okay, so we're going to start with this difference. And so R star is going to be, it's just defined to be that marginal. It's the marginal that we're claiming achieves the minimum. And R is any arbitrary distribution. Okay, so let's look at this difference. Okay, so this is the difference. This is the gap, if you will, the gap of the optimal to the current. And then this is just written as the expected log of the ratio, which when we express, since R star is equal to P of xy, we can express the joint using this form because of the way that we've defined R star. And this is then just the Kolbeck-Leibler divergence between these two. This is the definition of the Kolbeck-Leibler divergence between a conditional distribution is equal to the expected value with respect to the joint of the ratio of the two conditionals. That's by definition. Everybody remember that? And we also know that the Kolbeck-Leibler divergence is never negative. So that basically means that the left side is greater than or equal to the right side. But then on the other hand, we know that we achieve equality whenever they're equal. So therefore, that's the optimum. It's a very simple proof. That's why I'm going through it. We're only going through the simple proofs today. The hard proofs we're skipping. Like I said, because last time we spent a week and a half on these proofs. And I don't think there was a single person who enjoyed going through those proofs in class. So you guys are benefiting from hindsight. Hindsight is 20/20. So, but here's an interesting way then. So let's use this theorem now. So here's an interesting way of writing the rate-distortion function. So we've got the rate-distortion function, which now here's its definition, right? And let's just expand out the mutual information using its definition. But now that we have this way of writing the mutual information as a optimization problem, in particular, in this case, a minimization problem, we can replace Q of x hat with R of x hat and take it and minimize over it. Okay. So all we're doing is, if this isn't clear, we've added this min over R of x hat. what we're able to do, as I'll argue in a minute, is we can swap the two mins. Right? And then you can see now that we've got two mins. We've got the outer min, the min over r x hat. We've got the inner min, which is over these conditional distributions that satisfy a distortion constraint. And then we've got this other thing here. And the thing that's written in magenta is really just it's just what? It's just the Kullback-Leibler divergence. Although I'm not going to use magenta, because for some reason magenta doesn't really work very well here. Let's use this color. That's a little better. So it's just the Kullback-Leibler divergence. Inside the curly brackets is just the KL divergence. All I've done is multiplied up, bottom, and top by P of x. So this now looks like an alternating minimization kind of thing. Maybe we could alternate between optimizing r of x hat and q of x hat given x, and r of x hat and q of x hat given. Maybe, is that going to work? Well, first of all, why can we swap the mins? The minimization, the swapping of the mins can happen essentially thanks to convexity. Everything's convex, and we've got a convex set of constraints. Negative log of r of x is convex, x log x is convex, and we're minimizing it over a set of linear constraints. So because of that, we can swap the mins. And so that basically means that the rate distortion function can be written as this alternating minimization form. We can write it either as this form or as this form, right? Where A and B are sets, right? So what is the set A? So A is basically all joint distributions P of x hat such that P of x hat can be written as this factorized form where it's Q of x hat given x times P of x. Now, what's important to realize about this particular constraint, in case that's confusing, is P of x is always going to be fixed. So we're varying. We're allowed to change this guy. We're defining the set by saying it's all joint distribution set can be written this way and this way. But this guy here is fixed. What's really varying is this conditional Q of x hat given x. Okay, and then the constraint is that resulting joint distribution must be such that that it satisfies the distortion constraint. Right? The expected value of the distortion must be less than or equal to d. Okay, and then secondly, set B is written in the same form. It's basically, again, a set defined by joint distributions over x and x hat. And this joint distribution must be factorizable, again with P fixed, but R is what we vary. All distributions R of x hat is really what we're changing, but we're thinking of it as a set of joint distributions. Okay, so it's factorized, and so that basically gives us what we want up here in the KL divergence guys. Up here. Okay. So what we can do then is to compute the rate distortion function very, very easily, starting at some point s, which is again the slope. We start with some hopefully arbitrary r of x hat, and find the corresponding conditional distribution. And we already have the formula for this, sort of sitting there. We already know this relationship. So we start with any arbitrary. We're going to see we're not going to be able to start with any arbitrary r of x hat. But the constraint on r of x hat that we're going to derive is going to be very, very easy. Namely, that none of the values can be 0. So it has to be strictly positive. But once we've got r of x hat, we can form Q. But then how do we do that second minimization? Well, thanks to that projection property, that's a projection, right? From the Kullback-Leibler divergence. How do we do that outer minimization over r of x hat? That's just a marginalization, because we proved that it's a marginalization. So that second optimization In other words, let's go back to that slide. This second optimization over B, might seem, oh, that's really hard, that's going to be tricky, but we actually know how to do that now. That's just basically this marginalization. So we just iterate back and forth, doing this, and then doing this, and then doing this, and then doing this, and we just iterate back and forth with those equations. And we do this until it converges, hopefully. Yep.
You were talking a few lectures ago about the history of this. Was this the original tactic that then you said later is shown to be equivalent to other people's ideas?
Yes, so, well, originally, the rate distortion function idea, this idea actually was outlined in the Bilmes and Aramoto papers that you're supposed to be reading. And it wasn't until Emir Sizar, who's this Hungarian information theorist, very famous Hungarian information theorist, published this paper in like 75 and then 76, and a bunch of papers I think culminated in 83, where in this series of papers he first showed that, because people were interested in, for example, things like convergence, and what were the conditions under which it converges, and how do you prove convergence, and when you know if it does converge, but that it is converged, and is there a way to stop in some practical way, and is there some more general framework within which this kind of thing works? And it wasn't until really Sizar in 83, although he really was working on it through the 70s, he sort of showed all of the things, sort of the proof of convergence, the convergence conditions, and that it's also equivalent to the EM algorithm. That was originally given in Dempster-Laird and Rabin, I think, in 1973. So it was sort of, so the actual step of doing this projection back and forth was outlined in the Bilmes and Aramoto papers, but it wasn't known all of these other conditions until the work by Sizar, and that this was an instance of alternating minimization. Now, people, like I said, people these days I've seen, like in the machine learning community, that sometimes they'll use alternating minimization without actually having a condition that validly allows it to converge. And again, it's important to realize that this is different than sort of coordinate descent, because the coordinate descent is something that sometimes works when you have a convex function. There's other conditions. Paul Tsang actually did a nice paper on certain conditions under which coordinate descent work under various convex cases and polyhedral convex cases versus non-polyhedral convex cases. But here we're not really. Well, the issue is we're not really saying necessarily that this is a only convex function, nor are we, although it does work for convex functions, nor are we saying that the sets have to be convex necessarily. Although in practice, it's always been the case that those are the ones that have been useful. But we'll talk about this. You'll see a little bit more when we study the more general conditions under which this holds. So we want to, and also what is D? What kind of function is D for this to work? Can it be arbitrary? Probably not. Although sometimes, like I said, people use this as a heuristic. A heuristic, when you say heuristic, it means it's just some idea that you have, and you say, oh, here's something I want to do. Let's just come up with this method. I have no idea if it's going to work or not, but let's just try it, and maybe it'll work in practice. And people have used alternating minimization for heuristics quite successfully without knowing whether or not it works or how badly it doesn't work if it doesn't work, and so on and so forth. So what we will prove, however, or we will actually not go through the proof, but we will state the theorem is that when and how this converges. But because we're going to be dealing with continuous measures, we have to delve a little bit into the continuous measure theory. But before we do that, let's look at channel capacity, because it turns out that this, and actually in the Bilmes and Aramoto papers, because they were they were primarily information theorists, they found that this kind of procedure also works for computing the capacity, the channel capacity function. So let's just recall what that is. We have a noisy channel. It has a capacity C, and Shannon proved this, that it's the limit of communication. We can only communicate at rates no greater than the capacity. We can only communicate with small probabilities of error. And so we can then express the capacity. Remember, the capacity in this case was an optimization over the source distribution. So in the rate distortion theory, the source distribution is fixed, and we're optimizing over the conditional distribution. In the channel capacity, the conditional distribution is the channel, which is fixed, and we're optimizing over the source distribution. We want to decide how much probability to put on each source symbol that we end up sending. And so what we're doing here is that the original max over R, this guy, is part of the original definition. Right, and here's the joint distribution. This is the original joint distribution we're trying to find. But what we're doing is an additional maximization over this conditional up here in the log. So in other words, this guy here is the true channel, and then this one here is what we're optimizing over inside of the argument. But that's a valid way, thanks to the property that we proved. That's a valid way of expressing the channel capacity function. And so as a result, we can go through and do a little bit of algebra, and we find a very, very simple way, again, of computing the channel capacity function. We alternate between these two equations. We first do that one, and then we do this one. Now the form of them looks a little bit different, right? So here, on the left-hand side, we're doing this conditional model. Basically, we're taking the joint and dividing by p of y, which actually was the projection that we showed was optimal in part 2 of the theorem that we saw a couple of slides ago. The right-hand side is actually sort of a form of like a harmonic mean, like a weighted harmonic mean. Or maybe it's a weighted geometric mean, I think is the better term. Because we're, in some sense, taking like a geometric mean of q weighted by p, and then normalizing. So it's not an arithmetic mean. It's like a weird form of geometric mean. But you just keep doing that, bouncing back and forth, and it will converge to the right answer, to the capacity. And this is something that's useful, because unlike where we can actually compute an exact expression for the capacity, imagine if the channel, you knew the properties of the channel, here's the channel again. I'm going to outline it in green. This is the channel. But let's say it's this massive matrix, and it's not necessarily symmetric, and doesn't have all these nice things that we used and we assumed when we computed the capacity analytically. But we still want to see what it is. We want to see how many bits can we, what's the limit of communication. And maybe the p of y given x is something we could even measure. We could look at the noise profile of a given transmission scheme, wireless transmission scheme. We'd find that it's expressed by p. Yeah, Scott?
I'm just trying to parse this equation. Why is there an r of x and an r of y? Remind me what, so r of x is like the distribution on the source symbols, right?
Yeah, so basically, yeah, that should be r of x. Sorry, you found a typo. Sorry about that. Let me do this in black. And let's do it in red. Sorry. That way I'll see it and fix it. Does that look better?
And one other question. Is
yep.
q of x given y, isn't that like the decoder?
It's not really. It's just this conditional distribution that we're optimizing over. Right? The decoder is basically, again, where we get this symbol and we need to come back. This is, remember, we have a channel code which basically goes from integers into x's, and then we get y's, and we need to go from y's back to integers. That would be really seen as the decoder. This is just sort of like a conditional distribution. It's like the reverse channel, but it's not really even a reverse channel. It's just the thing that we're optimizing over. It's just an expression. Because if we got rid of that outer max and we substituted this, then we would get the right thing. Okay, so okay, let's do this sort of this overall idea. So we've got these convex sets for right now, and let's say we've got finite measures, and so that basically means we have a set of measures. So for every member of P and every member of Q, we have that it sums to 1, and we have that it's non-negative. Okay, so that's the thing that we're optimizing over. And then we're going to define P of n. So P of n is going to be like a starting point, or this is for any n. It's going to be some point. And then we find what is the alternating minimization procedure, where we hold P of n fixed, and we optimize over Q in the Kolbeck-Leibler divergence. So here's optimizing over Q in the Kolbeck-Leibler divergence, holding P of n fixed, and we get Q of n. And then we just alternate back and forth. So we do alternating minimization, where we take a Q of n holding Pn fixed, and that gives us Qn, which optimizes this scale divergence, and then we take a P of n, which does this thing here. Okay. Now the other thing, of course, that we would need for this to be useful is that each one of these steps should be analytically tractable, and we saw that, for example, in the rate distortion case and the Kolbeck and the channel capacity case, each one of these optimization steps are in fact tractable. Now sometimes, in practice, you get all of the conditions are true for convergence, all of the nice mathematical conditions, except for the analytic tractability of these steps. So it may be the case that each one of these itself is an optimization problem, but on the other hand, maybe each one of these is simpler than, say, optimizing over the joint. So that sometimes happens. So the result that we're going to sort of outline, like I said, we're not going to go through these proofs in detail, but the result we're going to outline, and basically what is written, how it's written in Scissor's 1983 paper and some of his earlier papers, is that this sequence, let's just get an understanding of what he's actually asking for. This sequence is going to converge to the infimum of the Kolbeck-Leibler divergence over all measures P and Q that are in this set, P0 and Q. Script P0 and script Q. Okay, where script Q is the same Q, right? Q is just some convex set of finite measures, right? And P0 is kind of a funny set, but basically it's a subset of P. P0 is a subset of P, such that this Kolbeck-Leibler divergence is finite for some Q along the way of this optimization problem. So in other words, there has to be any P such that there is some Q in this particular sequence that we encounter that achieves finiteness is a valid P. And so we're also going to get that Pn goes to Pn, which is the two. So P star and Q star. We were using A star and B star before, but these are the true minimum. And then Qn is going to also, depending on a number of conditions, technical conditions, sometimes goes to Q star as well. Yeah, in other words, these are the distributions that achieve D-min. Okay. So the reason why we use this P0, I mean, this is again, Scissor, what he was doing is he's saying, okay, well, I want in general to come up with the conditions, the least set of assumptions about the thing that we're optimizing over in order to make it true. And so it turns out that these P0 guys are only those are the only ones that we are going to encounter. And those only ones we care about, so that's why it's defined this way. So you can think of it geometrically, because you can think of the Kolbeck-Leibler as a generalized distance in some sense, although I would caution you against ever calling the Kolbeck-Leibler divergence a distance, because it's not a distance. I've had papers rejected because I called something that was not a distance accidentally once in the paper. So it's something that one has to be a little bit careful about. especially in the mathematics community. So it's not really a distance. We'll talk about that in a second. But this idea, this also generalizes a number of problems, including the maximum likelihood estimation for mixtures, like for example, hidden Markov models, estimating the parameters in a maximum likelihood sense of a hidden Markov model, or other graphical models, or just a Gaussian mixture. That's the EM algorithm. So the EM algorithm is a very generic algorithm for computing the maximum likelihood over any graphical model where some of the variables are hidden and some of the variables are observed. And you still want to come up with a estimate of the maximum likelihood. We saw it sort of corresponds to the rate distortion function computation, or what's known as the Blehut-Arimoto algorithm. Also for computing the channel capacity function, which we saw. For certain investment portfolio optimization problems. There are a number of people in finance who are interested in this, and also a number of semi-supervised learning objectives in machine learning, including the well-known label propagation form of semi-supervised learning, and also measure propagation. These are both instances of alternative minimization that work. And so they really depend on this guy, and we're going to call this a quasi-distance. Right? It's a quasi-distance, that's for reasons that you'll see in a minute. So this guy here, this D, it's a function of two sets, P and Q, and it can map to R and to positive infinity. But it doesn't even need to be the K-L divergence. It can be any quasi-distance that satisfies a certain property, which we'll talk about. So remember from lecture 3, this is this notion of distance. From lecture 3, we said let x be any set function, and we have this distance, or function D is called a distance on x if on the one hand it's non-negative. For all x and y, it's never negative. D of xy is never negative. Number 2, if it's symmetric, so d of xy is equal to dyx. And number 3, if it's reflexive, d of xx is equal to 0. Okay, so that is officially a distance, and you can, if you have a two-argument function that satisfies these properties, you can call this a distance with impunity. On the other hand, a quasi-distance need only be non-negative and reflexive. Non-negative and reflexive. All right, so that's not a lot of constraints. We have other things, like, there's a semi-metric. A semi-metric is another form of one of these functions that has to be non-negative and symmetric and reflexive, and it has to satisfy this fourth property, namely the triangle inequality. So a semi-metric has this property, and then lastly, a metric is both a semi-metric, and if it has this other strangely named property, identity of indiscernibles. So in other words, do people know what identity of indiscernibles means? So that basically means that if two guys are indiscernible, if we can't discern the difference between x and y via this function, then they have to be identical. So it's the identity of indiscernibles. This is something that normally one would go over in the liberal arts courses, but I thought since we're a little bit closer to the English building, we might as well identify why it's called the identity of indiscernibles. But everybody now knows why it's called identity of indiscernibles. Right? Okay. So that's called a metric. So a metric must have that property. The Kullback-Leibler divergence, on the other hand, is not a distance. Why? Well, first of all, it's not symmetric, so it's definitely not a distance. It's not a semi-metric because it doesn't satisfy the triangle inequality, so therefore it's not a metric. But it is a quasi-distance, but it also satisfies the identity of indiscernibles. So it's really none of those. And so that's why, we generally like to call it a divergence, because it's sort of, although it's not universally used to mean a quasi-distance that satisfies the identity of indiscernibles. But
Is there a formal definition of divergence?
I don't think so. So I don't think there's a universal definition of a divergence. In information theory, this is what we mean by a divergence. It's just not correct to call it it. In topology and other branches of mathematics, there are broad, very, very broad. There's all sorts of different names. There's actually a fantastic, if people are interested, there's a fantastic book by whose last name is Deza, D-E-Z-A, called the Encyclopedia of Distances, and he goes through. He has several pages of probably about 50 different categorizations of these types of names. It's quasi-semi, half-metric, and semi-quasi pseudo-metric and pseudo-half. And it's a very, very broad. It's a very, very, very narrow, very specific terms for very specific things. I personally don't have a lot of them memorized. I have these ones memorized, but not the other ones. Okay, so properties of D. So what do we need for our D? So none of these are sufficient alone to allow alternating minimization to converge. We need something else, which was going to be called the 5 points property. So we could call it a 5pp quasi-metric that satisfies the identity of indiscernibles. That's what we need. So let's say that this is a. So notice that these are the other things that we only need it to be half extended real. So it can include infinity. So the Kullback-Leibler divergence can be infinite, right? But a Kullback-Leibler divergence is never negative. So it's sort of half extended real valued function, pairwise function. And then the first thing what we do, this is just a little bit of notation, this is scissors notation, is we're going to define this first optimization problem where we hold P, we're holding the first argument number 1, the one on the left, fixed, while optimizing over Q, and so therefore we're going to notate this as the following way. P goes to Q prime with a 1 over the 2, or I should say 1 over the arrow. And what this really means is that we're holding P fixed, optimizing over Q, holding P fixed. P is the first argument. And that gives us Q prime, which is the result of this optimization. And then similarly, we're going to use this notation. Where now what this means is that we're holding the second argument fixed, which is Q, but optimizing over the first argument. So remember, the number over the arrow is there's only 2 argument functions. The number over the arrow is the argument that we're holding fixed. And then we're naming that argument by using this name on the left. And then the result of that optimization is where we go to. So with this notation, and I think this was the motivation for doing this, you can write a sequence of alternating minimization in this fashion. So we start with a P naught, we optimize over Q, we get Q naught. Then we hold Q naught fixed, we optimize over P, and we get, we hold the second argument fixed and optimize over the first, and we get P naught, and so on and so forth. This goes on forever, starting arbitrarily with some P naught, say. So we want to try to sort of begin to understand the conditions of convergence. So here's the 5 points property. So we've got a quasi-distance, and it's again extended. It's defined over the half-extended reals. So this is what we mean by the half-extended, because the real set doesn't include infinity, right? Everybody knows that. So we're extending it with plus infinity, just so KL divergence is included in this set. And it satisfies the 5 points property at P if it's the case for all Q and Q and Q not in Q. We satisfy this inequality. Whenever it's the case that this is true. So in other words, we have 2 things that we're optimizing over, P1 and Q1. Okay. But Q1 is dependent on P1, and P1 is dependent on Q0. So basically, the first optimization is where we're holding the second argument Q0 fixed and getting a P1, and then the second Q1 is dependent on holding P1 fixed and optimizing over Q to get Q1. So then we say that D, this pair's argument, satisfies the 5-point property if it satisfies the 5-point property for all P. So either the difference is either it satisfies it at a particular P or it satisfies it for all P.
This is just saying that your thing will converge if it improves every time you do, right? Like,
It's kind of saying that, yeah. I mean, we're going to use that. It's not saying it's not saying it improves every time. It's saying it sort of doesn't deprove. It doesn't get worse. Right? But this is a value. It's defined at P. But exactly because Q. We've got this guy's the next point. This guy's the initial point, right? So we're starting at P, and then we've got this Q. It's a little bit funny though because P and Q, there's no necessary relationship between P and Q naught. Right? So we need a little bit more than that. But like maybe you might think that there's a little bit stronger of a condition that requires Q naught to necessarily come from some previous optimization. But this is saying it has to be any Q naught. Right? So it's a property of a quasi-distance across sets. It's defined on 5 points, right? So what are the 5 points? And where does it get its name? Hopefully, you have 5 colors. So there's P. There's 1 point. There's Q. It's another point. There's Q naught. Another point. There's Q1. And there's P1. 5 points. 5 colors, 5 points. That worked out fine. I only have 5 colors, by the way, I can work with here. And you can think of it, I mean, it's not the triangle inequality. So the triangle inequality does not imply this. So a triangle inequality would say something like, for P1, P2, and P3, we need to have this to be true. If it was true, which is not in general. So it's not the same as the triangle inequality. But what I do have is a really nice picture that describes the 5 points property. So the first thing we do is let's take a point P. So there's P right there. Okay. Take a point P, pick a point Q, and pick a point Q naught. So we start out with these yellow points. We just choose them arbitrarily. Okay. So the first distance is basically this sum, right? It's d of PQ, which is this, plus d of P Q naught, which is this. Right? So we're just summing up those red distances, and that's what's like which is currently outlined in yellow and orange. Okay, so that's sort of just given. So that distance then has to be, the sum of those two distances has to be greater than or equal to the following. Well, first of all, then the next thing we do is we do the optimization. So it says, okay, well, we need to find P1. So we consider this optimization here, right? And P1 is closest to Q naught. Right? Out of all the points inside of P, P1 is the one that's closest to Q naught. And that's why if we zoom in a little bit, you can see that that's drawn as a right angle here, right there. Right angle to this orthogonal line. This is the tangent. So anyway, so we do that. And then we find Q naught, Q1. So then we find Q1, which is closest to P1 based on this optimization. But again, we consider all the possible points in Q, but we have to make Q1 closest to the result of the previous optimization, which was P1. And again, if we zoom in on there, we have the same kind of right angle property here, just to sort of draw this. And this is done in the context of a Euclidean space with convex sets. Right? So in general, we can't rely on this geometry and this geometric intuition to allow us to say, well, this is obviously the only thing. It turns out that there are other D functions which will still make it such that we've got convergence if the 5-point property holds. Because this is obviously not Kolbach-Leibler divergence, because Kolbach-Leibler is not a geometric, it's not a Euclidean measure. Does everybody get the idea?
So I know that the geometric interpretation isn't important here, but so I was just wondering why you chose to, like when you project or find P1 by fixing Q1, why you're going off the right angle of the tangent of Q instead of.
Well, this is the condition that's necessary. I forgot to say something that, if you look at this picture, we've got the sum of the red distances and the sum of the blue distances. And if we define all these points, as they're appropriate, so basically P1 is the closest point to Q naught, and then Q1 is the closest point to P1. And then the two blue distances are the distance between P and Q1. Sorry, I'm saying distance, and I'm going to get my entire lecture rejected if I keep saying distance. But let's just say this blue segment, the measure of the quasi-distance, how about if I say that? The quasi-distance between P and Q1 and summed with the quasi-distance between Q1 and P, that has to be no greater than the two red quasi-distances. Okay, now I think the intuition is again based on what you were saying, which is that it sort of corresponds, as we'll see, to an iteration of alternating minimization. So it means that we're not going to sort of go crazy. We're not going to go down to Pioneer Square and rip road signs off the. Which doesn't make any sense, does it? I think if you want to celebrate Seattle, what you do is you get really rowdy and clean trash from Pioneer Square or something, or paint. You do something positive for the city. To celebrate Seattle, you do something that would be beneficial, right? Wouldn't that make more sense? Destroying property. I mean, you usually do that when you're protesting something or you're angry about something, not when you're happy about something. I don't understand that. But in any event, what happens here is that you're doing something that ends up being useful for the alternating minimization procedure, because it corresponds kind of to an iteration of it. But geometrically, it doesn't. It's not as clear cut as. You can see that this obviously holds in this Euclidean case where we're using sort of Euclidean distance and we've got convex sets. And this may not be such a useful property for that. And in fact, if you look at the label propagation algorithm, that's in fact the reason why it corresponds to alternating minimization is because essentially they're using Euclidean distance. Measure propagation is another semi-supervised learning algorithm which uses the Kolbach-Leibler divergence. So what we want to do is we want to prove that if the phi property holds, either for all P and P, which is sort of the most general condition, or some other more technical condition that I'm going to specify a little bit later, then when we take the limit of this sequence of pairs that arise from alternating minimization, that's going to equal d min, which is the minimum. As long as this is that's not stated correctly. That should say is not negative infinity, and again where P naught is this condition, it's sort of this set of P's that are such that the Kolbach-Leibler or the quasi distance is non-infinite for some Q along the way. So I guess the critical thing is that P naught does depend on the sequence. And if D is, by the way, I should say if D is finite valued, unlike the Kolbach-Leibler divergence, if D happens to be finite valued, we don't need this technicality. We can just say it's all P. So that means that even in the Euclidean case, if you were restricted to sets for which it's always, a finite, a closed Euclidean case with closed convex sets, then we could use all P rather than P naught. So first of all, let's just define a little bit more notation. Actually, you know what? I think it's probably time for a break. So let's take a short break. And like I said, there's going to be a number of theorems that we're just going to write the theorem, and we're going to skip over like many pages of proof, and that's the thing that ended up taking like an hour, each one of those proofs. So I'm not going to do that. Okay, so here we are at part two. Is that where we are? Okay, we're just going to define notationally this idea, so that when we take this quasi-distance between two sets, what we really mean, just notationally quickly, is as the infimum over all points the infimum of the quasi-distance between all points within the sets, which is this part on the right-hand side right here. And note that it can't ever be negative infinite. That can never happen. So the first basic lemma is actually fairly trivial. It basically says that if you take a particular set of sequences that could be generated any way you want, not necessarily via alternating minimization, that the distance between the sets is going to be lower bounded by the distance between the sequences. And again, the key thing is that P naught is generated based on that sequence. And that's sort of an obvious thing, just because we're just minimizing overall items in the set. Okay. So what we want to do is identify when the sequences do converge down. The reason for doing this is that we can take differences between them, and it'll always be non-negative. Right. So does anyone remember the definition of lim sup? So what is the lim sup? First of all, the lim sup is not the limit. Okay, the lim sup, what it really means is the infimum of the supremum. Right, so first of all, what is the supremum? So the supremum is basically, you've got a set, right? And the supremum is the least upper bound. And it could be the set that the set corresponds to an open interval, right? In which case there is no max, right? But so you sort of have to leave the set. You have to close the set. And so the supremum is sort of for the instances where you're not closed. And so we take the supremum of all sequences. Let's go over to the right here. Take the supremum starting at n over all a sub k greater than n. And then for each n we have essentially one of those supremums. And we want to take the infimum, which is the greatest lower bound. And that's what the lim sup means. So you can also write it in this way. It's like the infimum of the set S, where S is basically all A such that A is equal to the supremum of B for some n. So we have like this set S, which is a bunch of these different supremums, and we take the infimum of that set. So that's the lim sup. Here's an example. So while the sine function, like if we take the limit as x goes to infinity of sine of x, that doesn't exist. But the lim sup of sine does exist, right? Because no matter how big x gets, the supremum of all of those values for in the future are going to be 1. And then we take the infimum of that, and that's going to be 1. The infimum of a bunch of 1s is going to be 1. So sine doesn't have a limit, but it does have lim sup. By the way, I like this definition. Sometimes people say, "Oh, what's the lim sup?" It's the limit of the sup, and that's sort of a cop-out way of describing it. I think you really need to think of it in this formal definition. It's the infimum of the supremum. Then it suddenly makes sense. I remember that once. I took a class. I think it was in an undergraduate class, and it was the first time I encountered lim sup, and the professor said, "The lim sup is just the limit of the supremum," and then went on. And I was very unhappy with that description. And it wasn't until I went back and looked it up and I realized actually that was not a correct description. So secondly, what is the limb sup of this thing? So here's another oscillating function, sine x minus sine squared x. I think this would be a hard one to guess, but would anyone like to?
Sine x minus sine squared x.
Yeah.
I'd guess either 0 or 1 or negative 1.
No, it's actually 1/4. But, I mean, the point is that there's this oscillating crazy thing. And it turns out that if you take the supremum, all of the supremums, and then you take this, the greatest lower bound of all the supremums, you get 1/4. It goes like, it wiggles around, and then, another way you can think of it is like if you put a line below it, and what's the first point it's going to touch? As you move a line up from the bottom, what's the first point it's going to touch? So, anyway, it allows for oscillation, and we only require sort of infimum convergence at the local maxima. So like, we've got a bunch of all these local maximas, and we only need, in some sense, the greatest lower bound of them to converge. Convergence in limb sup.
Quick question.
Yeah.
And this is a dumb question. Why not just call it the limb sup?
I don't know. I don't know why. You'd have to go back into the early analysis literature, which came out in the 1920s and 1930s. And this goes way back, so I don't know. It's a good historical question. The limb inf is really the supremum of the infima. You call this the sup inf. It's called the limb inf, and you see this everywhere. I mean, everywhere in analysis literature. So this is sort of the same thing. It's like you take the lower bounds, and then you take the supremum of all these sort of lower bounds. Okay, so here's a theorem. This is a theorem that I actually proved in class last time. And just the statement of the theorem is going to take us a while. So let's say that we have AN and BN, and we have extended real sequences in the sense that they can take real values or possibly plus infinity. And again, the plus infinity comes about because what we ultimately want this to be is essentially valuations of the Kullback-Leibler divergence. And let's say that C is some finite value, and let's say it's the case that this inequality is true for all n. So this is now a requirement on this sequences, that C plus Bn minus 1 is greater than Bn plus An. And also, let's furthermore assume that the lim sup of the sequence B is greater than negative infinity. And there's some point n naught such that Bn naught is finite. Obviously, immediately you can see that if there's a point n naught such that Bn is finite, everywhere after Bn is going to be finite also because of this property here. If Bn is finite and C is finite, it's not going to suddenly become non-finite. So then, what we're going to see is that the lim inf of An is going to be bounded above by C. And if in addition, we assume that the sums of these absolute values, so basically this is like saying, well, this is like a form of convergence to C, right? It's sort of different because we're saying that the sums of the absolute differences, the positive part. This is saying C minus An positive as well. So the negative parts don't count. Anytime it's negative, it doesn't count. It's only the positive part that's finite. It's basically saying that, at least from the perspective of Cn minus An, that's going to converge. So we're going to get a form of An is less than or equal to C, but written in a very different way. If that thing is finite, because it's a sum of infinite terms, then we can actually bound the absolute value of the differences, starting at n naught. And this is the critical thing that we'll need. So that basically, if it's the case that we sum an infinite number of terms and An and Cn are finite, that means that An and Cn must converge to each other in some way, in the way as it's expressed by this sum. And then lastly, we'll also have that the actual limit, the nice old-fashioned calculus limit of an is going to be equal to c. Okay, so very complicated to express this theorem. But let's skip the proof. Okay, so let's see I'm going to skip all these slides. I probably should have gotten rid of them. Okay, next theorem. In fact, this is the first main theorem. So if we've got a set of arbitrary sequences, Pn and Qn, for n going to 0 to infinity, that each come from P or Q, script P or Q, such that this 5 points property holds. So we're starting at P and Q, and essentially we express the 5 points in this particular way. So notice, first of all, that we're not saying that any actual minimization is done here. We're just saying that well, I should say there's no explicit minimization with respect to the 5 points property. It's only in the case that the sequences come from somewhere that happens to satisfy this. Okay. Then if either it's the case that for all P and P naughts, where P naughts defined, or it's the case that for some P and P naught such that this P here achieves this minimum. Like remember, this is the minimum over the two sets. Right? So if either A or B is true, then we have that this limit converges to the true minimum. So 5 points property is key, right? And if A holds, then this sequence is non-increasing. It's going down. And so it's actually getting smaller, which is good. And if B holds, then it's also kind of sort of getting smaller in this fashion. It's getting smaller in the sense that it means that it doesn't always have to strictly get smaller, but it can maybe go up and down a little bit. But the point is that this difference is going to be finite, summing over all n, starting at n naught, where n1 is some particular point, which, oops, I hope it's not at the end of the, right, there's some point n naught, which is down here, or n1, I guess it's written here. So a number of technical conditions that are required. So then this is the proof, which I'm not going to go over again. But basically what it does is it uses, I'll just very briefly outline it. What it does is it sort of equates the previous theorem, which is where all of the real, technical measure theoretic detail was needed in math and analysis. And it sort of equates these sequences to the AN, BN, and C, where C is this particular point here. And it shows that we get that. These first conditions. Like I said, I don't want to go through this. I would suggest going through the slides if you're interested. Okay. Any questions on the proof? I really, I was so, last time I did this, like I said, I spent a week and a half on these proofs. And I don't know why, I think after I'd spent a day and a half on them, I realized that it was a mistake, but then I felt like I can't stop in the middle, so I ended up spending another day and a half. So today what we're going to do, we're going to use this extra time and spend more time at the end of the quarter on network information theory. That's what I decided we're going to do. Yep.
So do most sensible distance functions satisfy the 5 points?
We'll talk about that in a minute. We'll talk about that. If you define sensible to mean those that satisfy the 5 points, yes, and then all of them do. All sensible ones do. So now we're going to consider a set of sequences that in fact do come from alternating minimization, starting at an arbitrary point P naught. So now we go back to this notation, which says that this is in fact a sequence of distributions that satisfy, or a sequence of points that satisfy alternating minimization. So then what that's going to mean is that we've got this, that this is decreasing, or it's not increasing. So let's spell this out a little bit more. So this is d of p n qn, where we minimize by p n plus 1. And this is just because of alternating minimization, right? So we have an ever non-increasing sequence. And then if the 5 points property holds for some p, and if we construct an alternating minimization sequence starting at p naught, then we're going to have the conditions of this previous theorem met. Meaning we're going to have, as long as we sort of start at a particular point, we'll have the 5-point property conditions satisfied, and therefore we will have the conditions of the theorem, and we will have the convergence consequences of that theorem. So here's an example. So let's start at n1. So we start at q naught, hold it fixed, and optimize over p1, optimize it and hold it q1, optimize it over q and get q1. So then we just immediately get the 5 points property from alternating minimization. And in fact, it seems reasonable to assume that the 5 points property came about from sort of looking at alternating minimization and say, okay, what's the least set of constraints I can impose on this d function for this to be true. So this is just sort of going through it. It's basically saying we optimize, since it holds for any q naught, it also holds for any q that was a result of some previous optimization. Like let's say we optimize, let's say the q naught came from some p naught, where we held p naught fixed and we optimized over q naught. So therefore it holds going backwards as well. And we have the same that's true when that q is the one that achieves this infimum, right? So then when we go to the next step, we also have the 5 points property holding as well. So the point of this exercise is to show that the 5 points property is going to continue to hold, guaranteed, if we keep doing alternating minimization. So starting at n equal to 2, so we start with this q1 here, right, which came from here. We optimize p2, and then we optimize q2, and that's going to be true as well. And since it's true for all of these guys, it's going to be true for the q1 where we previously optimized it based on p1. And therefore, by induction, it holds for all n greater than 2. And so we satisfy the conditions of the theorem, and therefore we have this property, which is great. But on the other hand, the 5 points property is maybe, as you've probably noticed, even when you have such a beautifully, richly expressive figure like the one that I gave to you, maybe we'd like to have something that's a little bit easier to find to be true, which would then imply the 5 points property. Because especially when you ask questions like the one you did, do all sensible quasi-distances satisfy the 5 points property? I mean, we don't know until we actually prove it. So it turns out that there are there's two additional properties which, if true, imply the 5 points property. And this will make checking the 5 points property much easier. And they're called the 3 points property and the 4 points property. So if the 3 points property and the 4 points property are true, then the 5 points property will be true as well. In fact, they're equivalent. The 3 points property and the 4 points property holding true is equivalent to the 5 points property holding true. But in order to do that, we need to know what is the 3 points property. Here's the 3 points property. First of all, it's 2 simpler, 2 units simpler in the simplicity scale, because it has 2 fewer points. But on the other hand, it's not quite 2 units simpler, because it does require this other weird function, which may seem strange to require, but it's necessary. So it's an additional quasi-distance function, delta, and it basically requires that it's a quasi-distance, right? So it's equal to 0 at p at the same argument, and it's non-negative. And then we have the d that we're trying to prove 5 points property on. And the 3 points property holds for p. If for all q, we just have this thing here. And again, we've got one step of optimization. So it's still the case that we have to do one step of optimization. P1 has to be optimized with respect to q naught, which is expressed here. So this is sort of like a reverse triangle inequality. Now, why is that? I mean, let's look at the picture for the 3 points property. So now we have only 3 points, first of all. Q naught, P, and P1. We choose a point, P. So we choose that guy. And we have to say, okay, for all Q naught, so we choose any arbitrary Q naught up here, anywhere from up here. I mean, let's just choose that one that's there. This one right here. And it's saying that the red distance, or the red quasi-value, whatever you want to call it, has to be greater than this quasi-value, which is equal to this, plus this quasi-value, which is equal to this. So obviously, we're drawing this with convex sets and Euclidean measure. This is not true. But this doesn't seem to be right. But it does very much depend on this d, right? This delta. So if we took everything to be the Euclidean measure, this wouldn't hold. But on the other hand, we haven't said what delta is. But the geometry would look something like this. And remember, the other thing I want to say is, again, P1. Where does P1 come from? So we've chosen Q here. P1 comes from this, it has to be this quasi-distance. It's the closest guy in P closest to Q. So the closest P guy to Q naught. So that's the 3 points property. And the 4 points property requires 4 points, surprisingly. And basically it says that it holds for P and P in script P, if for all Q and for all P1, so now we've got another point here, if this is true. And I think, again, looking at a picture is probably the easiest way of looking at it. So it says, choose a P, which is down here, and then choose any Q and Q, which is, here's the Q guy, and then any P1 and P in here. So those are the points that we get to choose for free. And it's again saying that the red quasi-distances, this ones, can't be less than the blue ones. It's this one. Where in this case, Q1 is the thing that gets optimized. So I didn't actually draw this tangent line here, the right line, but it's the same sort of thing. So right angle. Now, this is sort of the second main theorem that we want to define. So it's basically saying we've got this set of sequences defined by alternating minimization. Then this is true. We get this convergence. If either of these conditions are true, A or B, meaning that P is equal to P naught, or we start with P being in P naught with this being true, okay? And that has the 5 points property. And also, the 3 points property and the 4 points property imply the 5 points property. And if it's true, if condition A and the 3 points and the 4 points property are both true, then we've got something that's true about this additional delta function, which is kind of like another quasi-distance. So the quasi-distance guys are also decreasing. So P and P man. So the sequence of p's are getting closer and closer to p. So the one thing I want to do here in this proof, I'm not going to go through this proof, but there's one little bit here which I think sort of makes it easy to see why, at least intuitively, the 3 and the 4 points property imply the 5 points property. Because if you take the 3 points property here and the 4 points property here, and then we just add them up, this part is going to cancel out, and this part's going to cancel out. And we immediately get the 5 points property. So the delta function doesn't even matter. In some sense, it's usually defined. If you wanted to define it, you would define it by using these two equations and defining it in terms of delta in terms of d, and which basically requires some minimization. So delta can be defined in terms of d. You don't ever need to explicitly define delta. Although you can, but it's defined indirectly. But it does turn out to be easier in general to prove. So to answer your question, but again, about sensible distance, quasi-distances, you really can't know. I mean, oftentimes if it involves like combinations of Kullback-Leibler divergences of some sort, yes. But then sometimes, like I think a good example is the measure propagation objective, if you were to look at that. And that includes combinations of Kullback-Leibler divergences, some of whose arguments are fixed and not part of even P or Q. And it also involves some entropy terms. That's, can be seen in some sense as a Kullback-Leibler divergence, but that also involves, you can think of the entropy as the Kullback-Leibler divergence between a distribution and the uniform distribution. And so that again involves Kullback-Leibler divergences where some of the arguments are fixed. And so to prove whether or not the 3 and the 4 points property holds for an objective like that, you just need to prove it. So you can't just blindly say, I mean, obviously if you take convex mixtures of just vanilla Kullback-Leibler divergences, then it's going to be true. Or if you take conic mixtures, in fact, where the conic coefficients are fixed, then it will be true. But as soon as you get a little bit trickier by fixing some additional arguments or some other parameters that aren't trivially sort of additive in this sense, then there's nothing. You can't resort to it being true. You can't assume that it's true. You have to prove it, which sometimes is a little tricky. So the rest of this proof I'm going to skip, because I don't think like I said, for the rest of this class it's not that critical. So anyway, what we've got is that we've got this convergent set of sequences. Ideally what we'd like is that this minimization on the left, because remember, this is all with respect to this P0 sequence. And remember, P0 is basically something that's defined with respect to the sequence. And what we'd like it to be is that this is equal to the true minimum. And this is true whenever D is finite. But for the Kullback-Leibler divergence, that's not true. It's not necessarily finite. So it may depend on the starting value. And so getting a good starting value, it turns out to be, if we assume that P and Q are convex, these are measures, then if we take P0 to be strictly positive, it can be anything you want as long as it's strictly positive. And if there exists some P such that this is also trivially true. If there exists a P and a Q such that the product is strictly positive, which is always going to be true for measures, right? So in other words, if your sets are not constrained such that you have this sort of positive incompatibility with respect to each other. So what are the conditions? Condition 1, you need to be strictly positive in your starting point. 2, you have to be, and usually you don't have such conditions. Usually you don't have any a priori constraints about the interactions between the positivity of P's and Q's. You just say, sure, any probability distribution is fine with me. Then this set, has the property that this is true. That, in fact, we do get the true global minimum for overall P, overall in this case probability distributions. So all you need to do when you start this alternating minimization procedure is make sure that none of your probabilities are 0. And that guarantees convergence. If you start with 0, if one of them is 0, like if you do a random initialization, make sure that your random number doesn't give any possibility for 0. So that's a sort of a practical tip. Because I know you're all going to go out and start implementing this after today's lecture. So here's an example. I think it's worth doing this example. So this is the Euclidean distance. We can take d and delta both to be just the squared 2 norm. So this satisfies the 3 points property since the squared Euclidean distance has the following property, that it's always going to be greater than this minimization is going to have this angle which is always greater than pi halves, this angle down here. And I guess this is sort of a little bit restatement of that. So the 3 points property, I mean, I guess another way you can look at it is you can say, why does this hold? And it holds because if you actually take the squared Euclidean, the squared 2 norm, you can express it in this way. And what we want to show is that this thing is never, we can show that the 3 points is true as long as we can show that this guy here is greater than or equal to the sum of these two guys, which is true as long as this guy is greater than or equal to 0. I think I've got that written down somewhere. Right, so if this is greater than or equal to 0, then it's true. And why is it true? I mean, you can sort of geometrically look at why it's true. Because again, based on the minimization, P1 is the minimization in P closest to Q naught. And this is going to be a dot product. It's the dot product between this vector and this vector. And the angle, because of the convexity of the sets, this angle is always going to be greater than pi halves. Okay. So therefore, this quantity is going to be non-negative because of the angle between P minus P1 and Q naught minus P1. Okay, so you can also show the 4 points property. Here's a picture that sort of demonstrates why, but I think I'm going to leave this as an exercise. So your exercise is to prove the 4 points property is true for squared Euclidean distance. And that's not a difficult proof, but I mean it's not as difficult as some of the proofs that we're skipping. But this will sort of get you into sort of thinking a little bit more about the 3 and the 4 points property. And this is not the Euclidean distance, this is the squared Euclidean distance. Right, so emphasize on the squared. So it's not our usual notion of distance. It's a squared distance. So therefore you can use squared distance, you can run alternating minimization at squared distance. We also haven't required the sets to be convex. I wanted to end today's lecture. So let me just see if there's anything really critical. You know what, I'm going to skip over all of this stuff. The thing, what this material is really about is notions of a Raycon-Nikodine derivative, and also this notion of absolutely continuous with respect to one distribution with respect to another. And the basic idea is that, you know, for the Kohlberg-Leibler divergence to not be infinite, we use this notation, and this is a fairly elaborate way of saying that whenever Q is 0, whenever Q of x is equal to 0 in the denominator, P of x is also 0. And that it's okay if both of them are 0 because of the limit, because 0 log 0, the limit of x times log x over x as x goes to infinity is just going to be 0. But the problem happens is if Q of x is equal to 0 and P of x is not equal to 0, then we're going to get the infinite, the Kohlberg-Leibler divergence. So in the case of convex sets, we actually can define this based on the Kohlberg-Leibler divergence. And in the case if it's a probability measure, we've got that these things are equal to 1, so that we get back the standard Kohlberg-Leibler. Let me just get to the statement of the theorem. That the 3 points property holds in this particular setting that we're in terms of the Kohlberg-Leibler divergence and probability measures, even if it's the case that they're not normalized, which for most of the time they are. So this stuff here cancels out. So I'm going to skip this theorem also. Like I said, we went over a lot of this. And then we also have the 4 points property holds. And so therefore, for the Koblach-Leiber divergence, which we saw we could represent the rate distortion and the channel capacity as an alternating minimization optimization over, we have that we've got convergence of alternating minimization. There's one last thing I want to know, which is the stopping condition. So that turns out that this, I'm just going to state this last result. So basically, this is the optimum result here. Here's the result, here's the current value. And if we can put an upper bound on this difference, then we'll know when to stop. We can say, okay, well, we'll stop once we achieve numerical equality. And that, a fantastically wonderful upper bound on this is just the maximum ratio between two successive distributions. So we take two successive distributions of two iterations, and we take the maximum ratio of these things, and that's an upper bound. And if that thing gets small, then we know that the true difference that we want gets small. Even though we don't actually have the true minimum. The point is that we don't have this right-hand side that I'm going to outline in green. We don't have that guy. But we can still upper bound him, and therefore have a condition for convergence. And in practice, I should say, after implementing this myself, basically, this works really well in practice. So the other last thing I want to say is that we're not in general guaranteed that each minimization is going to be easy, but as we saw in the rate distortion case, each minimization is easy. In the EM algorithm, each minimization is easy. That's one of the reasons why people like the EM algorithm, because you can do each optimization, each projection in some sense very, very simply. For alternating, for rate distortion and channel capacity, it is the case that it's easy. Measure propagation also, and label propagation both have very, very simple updates. Okay, so that's all I'm going to say about alternating minimization. I mean, alternating minimization is a very, very general technique that can be useful for you in a lot of applications. What we're going to do next time is we're going to, I really wanted to end today's lecture with this, and I'm sorry for rushing through this last bit, but hopefully you'll go through the proofs and the slides. If you have any questions, contact me. But next time we're going to start a completely different topic, which is information functions in general, more general than entropy. And it's a really interesting topic, and it gets back into a little bit of the sort of philosophy behind information theory that we touched upon a little bit last quarter. And we will finally, at last, begin to introduce this magical number omega that I've been warning people about, the number that has the answer to every single question. And we will define that eventually, probably not next time, but maybe the lecture after that. But if you want to understand omega, if you don't come to next lecture. So next lecture is critical. Okay, see you on Wednesday.